I'd like to thank the organizers, especially Doreen and Jill, for organizing this wonderful conference. I've been here twice, but that was more than 15 years ago, so I really enjoyed the chance to be able to come here and visit this university again. And I would like to talk about some recent joint work with Giulio Cirabella and Yan at Tsinghua University. And basically, the topic is about exploring what's the ultimate limit of the quality of quantum cloning. And especially, we would like to resolve the question for an important family of quantum states, and also with probabilistic cloning. And of course, replicating information is a basic task. And classically, we know how to do it in various forms. And the subject of quantum cloning is that is it possible to achieve the same effect for microscopic objects that are quantum in nature? And now, we all know there's this famous theorem of no cloning theorem of Wootters, Zures, and Dieks in 1982. It says no physical process can copy an arbitrary state and produce an output more than one copies of the original state. So in other words, if you want to have such a cloner, you would not be able to do it. And now certainly quantum cloning is something of a lot of interest, both as a matter of fundamental question and also applications, because it does go to the root of the security of quantum cryptography, the possibility, and also the trouble in designing quantum error correcting code as compared to the classical case. And now, since the advent of the no cloning theorem, a lot of effort people have studied beyond the no cloning theorem. What can we say about cloning? And there are several different ways that one can get around the no cloning theorem. For example, one would like to consider what's the best way to do approximate cloning, I mean for arbitrary state. And another idea is that suppose you allow probabilistic algorithms so that you don't expect to succeed all the time, but you do hope that when you succeed, you'll be able to produce very high quality clones. And a third one is that instead of cloning arbitrary states, perhaps we are interested in cloning some family of more restricted states. And so there's a lot of literature, but typically they are more on a case-by-case basis. And so the question we would like to address is that is it possible to have some general rules that have some general applicability? And in particular, we are particularly interested in the probabilistic cloning because I think that probabilistic cloning is something that is a little bit more difficult to deal with, and there are less results known about the efficiency of probabilistic cloning. And so the plan of the talk will go back to the origin of the no cloning theorem, where some of the concepts like probabilistic cloning started to appear, and then we're going to give a formal definition what it means to replicate the quantum information, and then we're going to give a derivation, at least an informal derivation of what is the limit to the replication rate. Actually, interestingly, it's the hint came from quantum metrology, and then we're going to show that these bounds can actually be achieved, and then we are throw some caveat about how good these algorithms are. So I think I wasn't aware of the origin of the no cloning theorem until recently, and I thought it's very, very interesting. So I will share it here. I think that so it started out by a paper by Herbert in 1982, where he claimed that that it's possible to design a device so that it's possible to have a greater than speed of light communication of information. And of course, it's not to be the case. And however, it's interesting to see how it went about. So the setup is the following. Well, we all know in the entangled pairs, if you have two entangled photons, then if you measure Alice, the photon, in arbitrary polarization direction, then it will determine what the state of the other photon is. And so this happens no matter which direction that you pick. And now Herbert's idea is that he has an amplifier, and he said that, well, let's produce this entangled photons, and Alice and Bob each keep a copy so that they could be at a very long distance away. And now Alice can do a measurement choosing an arbitrary direction. And now the other photons will be, of course, we know, instantaneously becoming polarized in the opposite direction. And so now if you use a idealized laser tube that it has a gas of excited atoms, then because we know that there are this stimulated photon emission, so that the single photon will be able to simulate a lot of atoms and produce identical copies. So there will be many of these copies. And now, using this amplifier, then Bob will be able to discover the polarization of this photon and will be able to discover the direction, because now Bob has many copies of these photons to deal with. Now, of course, the problem is that physically the atom will also spontaneously emit photons of random polarization. So on the average, you will not be able to achieve what you would like to do, because the quality of the copies will be so bad. And now how about the probabilistic thing? Is it possible to imagine that you have a quantum version of the Maximus demon that will just sit there and try to separate the photons from the stimulated emission from those generated by the spontaneous one? And now, with a very small probability, this could generate an arbitrary number of perfect copies, and hence we will get around the problem that we had before. But of course, we kind of know that this is not possible, because even in principle, it's really not possible to discover which photons are produced in this fashion. Now, but nonetheless, the idea of using probabilistic algorithms to do interesting information processing tasks lived on, and so in particular, when you produce in the abstract, you think about a cloner, you might consider processes that succeed sometimes, and this is called probabilistic cloners, and it was raised by Duan and Guo in 1998, and so that they did achieve some really interesting result, namely that actually, if you have a family of sometimes if you have a system of linearly independent states, then it's possible to have a probabilistic machine that can clone in the probabilistic sense. And now, however, we know that certainly the dream of using probabilistic method, no matter how you use it, is not possible to do the perfect cloning. So therefore, as we said in the beginning, there are a few ways to try to do the best we can. Namely, you can try to do approximate cloning, you can try to do probabilistic cloning, and you can try to do restricted set. And probabilistic cloning actually sometimes do very well, as you can see that in prestigious journals that they are reporting that sometimes you have heralded type of events that actually can improve a lot over the deterministic way of doing it. And now, so the interesting question, especially for computer scientists, is just to, when you're faced with probabilistic process, you really like to know that how does it differ from the deterministic one. Can you improve things in a qualitative sense? And so this setup, what we would like to do, we want to understand in some way the laws that govern probabilistic process for cloning, and we like to find the ultimate, in particular for the quantum replication. And so now let's set up the model. This is a standard model. The replication process that you have a certain collection of states indexed by theta, and you would like to transform n perfect copies into m. So m supposed to be bigger than n, and but you allow these copies to be imperfect. And the quality of copies can be measured by different ways. And one of the reasonable criterion is to use the global fidelity, namely that you look at the output of the states and you look at how much it overlaps with the target that you would like to reach. And we would like that we define a process to be reliable if when n becomes large. Then m is a kind of, we set to be a certain growth rate of n, and that the reliable replication means that when n becomes large, the fidelity would go to 1.
Sorry, may I just ask a question? The overlap here, doesn't these two states have different dimensions?
No, this is the output. So the target is in it's the space of m of these states, and the output after you do a quantum transition, it will come out to be a state in the tensor product and m time space. So your process will go beyond the original. So you put some ancillary, so that in the end you would produce things in the same state, in the same space.
So does that integral mean so you're taking the average copy?
The average
over all the states that you might create?
That's right. That's right.
In some set that you have.
Yeah. We are, because we are particularly going to be interested in a family which has this symmetry, so that okay, the average is sort of the same as the worst case. And now I think as a standard it's possible to write it in terms of the replication rate. But what it says is that if you look at the extra copies that you are able to produce, and let's see that what's the highest power that you can get. So the rate is linear. If you have n copies, you can produce another n copies. Now this is a linear number of copies, and we'll say that the rate is achievable if there exists a reliable process with that rate. So if alpha is less than 1, then it means that the number of copies additional that you can produce is very small compared to the original one. But alpha is bigger than 1, then it means that you are copying with a very large number of copies. And now the example in this terminology, if we look at what we know the universal qubit cloning pretty well, and it's been known for a long time that the optimal way for arbitrary state to clone it's the ratio between n and m, and so what it means is that if the rate is less than 1, strictly less than 1, then it's achievable. If you are only interested in n to the alpha, say square root of n, additional copies you can achieve reliable replication. But if you want to copy more than linear, then it's not achievable because of this formula. They have to go to 0. And so the number of extra copies have to be negligible in the universal case. And now, so if we define the replication capacity to be the maximum of all the achievable rates, then we know a few things from Werner's result. We know that for arbitrary qubit states, this number is equal to 1, and actually he proved for in d-dimension states it's equal to 1. And also there are indications for, even if you are interested in only a subset of the states, for example, the family of equatorial qubits, but then you can only achieve linear efficiency. So the question is that now, to what extent is this true? And also, what about for the case of probabilistic cloning? And so now we would like to first derive some upper bounds on what can we possibly achieve at most. And then we are going to show that these bounds can be achieved. And we are going to show that a hint on what are the achievable rates actually come from quantum metrology. So we will be exclusively be interested. Yes.
So the theorems that you showed, it looks a lot like general capacity information theory and so on.
Yeah.
Right? But in those scenarios, you have a source that emits symbols, and so it makes sense to think about the limit as n goes to infinity, because well,
Yeah.
you can guess what means it's
Yeah.
natural. But here it looks like what you're suggesting works when you take a very large Hilbert space.
Yeah.
So but it's much more difficult to create,
Yeah.
in the lab.
Absolutely, absolutely. So I think that certainly when we talk about asymptotics, if you want to realize it in the lab, then you have to look at the numbers and see what it comes out. And I think that what we have done here, I think is not particular. You will see that we'll have a caveat in the end. So I think that this really is more theoretical in terms of the intellectual curiosity on what asymptotically can you achieve. But my understanding is that actually the number of copies you can gather in the lab is very small anyway. So I think that to do things that are really useful for the lab, you have to look at the individual numbers. Okay. Yeah.
Maybe you talk about it. Why is there was this initial paradox that the non-cloning theorem resolved? Why this paradox does not hold for this probabilistic cloning where you produce a small number of extra copies?
In all cases, we are dealing with approximate cloning. So the clone will not be perfect. So it's, whether it's deterministic or probabilistic, we have already set the framework that the clones cannot be perfect. But we are interested in the fidelity.
This imperfection already kills the paradox?
Already what?
This kills the signaling paradox?
Yeah. Yeah. Yes.
I'm not sure I understand the measure, but if you're able to clone, say, square root n qubits of extra copies,
Yeah.
and then you can repeat this again. What collapses if I try to replicate the bound again and again?
Yeah, I think that that's a good question. I was ready for it for after the talk, but basically we are focusing on the probabilistic case, and so in those cases, when you look at it, that the success probability is very small. It's exponentially small. So that makes it that you cannot, because even though when you succeed, the fidelity, the copy look like the real ones. However, they are in an exponential sense, they are not the same. So therefore, you will not be able to saying that if I apply an arbitrary process, I will achieve very similar result as the true copies. So even though that if you do some linear thing, do some simple things that they look like behaving like the true random good copies, but if you probe it, if you say, do an exponential computation or something, you will find out they are different. Okay. Yes.
Maybe it's related, but just comment whether it's like when you clone, you also affect the original system. The original system usually changes.
Oh yeah, the original system is gone.
So you get two new copies. It's not that you keep the original system at the original.
Right. Everything is affected. We're not obliged to keep the original copy. Yeah, so actually they have to be changed in order to achieve good result. And so we are interested in this clock state. So essentially, these are the states that in the quantum metrology, if you measure the phase, I think this is the family that we are particularly interested in. And so this includes the examples such as the linearly polarized photons. But this Hamiltonian, it could be any Hamiltonian, and but it's a Hamiltonian on a fixed dimensional space. And when we let n goes to infinity, this space, the dimension, stays fixed. And also, the only thing we require is that this h is non-trivial, so that it's not the identical Hamiltonian. And now, what we can prove is the following upper bound. It says that if for this set of clock states, the replication capacity for the deterministic process is bounded by 1. So linear is the number of copies, is the upper bound on what you can achieve. And you can at most produce a quadratic number of extra copies if you use the probabilistic cloning, so that you can be sure when you get the signal, it's going to be a really good quadratic number of copies. And so as a corollary, it says that for the deterministic process, you can only really produce a negligible amount of replica in the asymptotic sense. And even you allow probabilistic case, then the upper bound is going to be quadratic. And so in our notation, the alpha star is less than equal to 1, and we call it this is obeys the standard quantum limit, and for probabilistic case is bounded by 2, and we'll call it the Heisenberg limit. And the reason that we say so is because we're going to give you a derivation from the quantum metrology, the Heisenberg limit, in order for the theorem. So let's look at the quantum metrology. So I think that there are a lot of discussions about the Heisenberg limit. I think that depending on what you mean, that but we are interested in a very limited simple version. So there is no real controversy here. So in our setting, for the standard quantum limit is the following thing. You have n copies of the clock states, and you would like to measure the parameter theta. And the variance, I mean, for example, you might measure each of these copies individually, and now you take the statistical average. And so it turns out that for this type of approach, as long as you have the input is the n copy of independent of these clock states, and you determine the parameter, then the variance is going to vary. It has to be bigger than 1 over n. So in other words, the standard deviation would be like 1 over the square root of n. So it's sort of like the classical statistic computation. Now in the Heisenberg limit, what it means is that suppose we have this n clock state, but we are allowed to do operations on them and do the measurement. And so in particular, we can have a process that make projections of these n copies, making them entangle and then do projections, and use that in order to do measurement with a suitable entangled state. The variance with scale could be 1 over the n squared. So in other words, if you allow entangled method, then to prepare the states in entanglement, then it is possible to produce a accuracy instead of 1 over square root of n, but you get 1 over n, and that's the best that you can do. And now let's see what the implication is for this Heisenberg limit and quantum standard limit on for our case. And I think intuitively it's pretty clear what we would like to do. And the idea is that if you can replicate the state reliably into, say, quadratic number of copies, and then you will be able, say, for each individual copies, you can measure them. Because if they are really close to the product states that you intend to do, then if you measure this n squared copies individually, and assuming that they behave like the product states, the perfect target state, then you will be able to get 1 over the variance could be 1 over the number of copies. Okay, so this is the idea, but now this also applies to the to the standard quantum limit. But I think that here one has to be careful, especially for the probabilistic case. And the reason is that you cannot assume that the copies that you get would behave exactly like the target states, and only you don't try to manipulate it too hard. You will be able to use the argument. So there is some subtlety that needs to be careful in order to make the argument. So.
Can you explain that again? If I understood right, you're trying to say, why can't you say that the Heisenberg limit will be broken the same way like the standard quantum limit, just by replicating? And you said that there's some subtlety.
Yeah. So the point is that if I because ideally what you will say is that right now I probabilistically produce all this kind of something that behaves exponentially close to the true product state, and let me just pretend that these are the really independent state, and then I try to replicate it again, right? I mean that's what you're saying, right? But
It's clear that if it will be perfect copies, then the Heisenberg limit will be broken, right?
That's right. But the point is that if you try to entangle them and do projections, you are manipulating in such a way that you can tell it's different from the true copies. So I think perhaps it will be clear after I explain the subtlety in the next couple of slides. Okay. Now, so here's a little bit more detail of this argument. So let m equal to n plus the extra n to the alpha copies, and so let's first do it for the standard quantum limit, and also let's assume that we are interested in producing copies that are not just 1% away from the fidelity 1, but actually also it's so close it behaves like 1 over m. Okay, so I'm putting this here so that the argument will work, but that particular constraint can be thrown away later on. Okay, so let's assume that the copies that you produce, it's really good. It's very, very close to the target state, so that somehow their difference is very negligible if you do the standard thing. And so so here's the input, and you have a deterministic quantum process that obtain the output, and it's the trace distance with the product state. It's bounded by more than 1 over m. And now the variance of the if I try to measure the parameter theta using these states. So it kind of in the same way as before. Take the best standard limit variance that you can, the optimal way to do it, and let's do it for this thing here. Then you can see that the variance that you produce is bounded by the variance coming from here and plus this, because the trace distance being very close, it put an upper bound on the statistical distance between the two copies. So therefore, the variance is just a linear in terms of the amplitude of the probability of the different values of theta. And now, so in other words, what we are doing is that in essence, this measurement is also a measurement of that is allowed by the framework of the standard quantum limit. We have these product states, and we just do a little manipulation, and then we get a. So this is one of the process, and this has to be bigger than the minimum that can be achieved. Okay, so all this process is exact quantification of the intuitive idea that if I can produce a lot of additional copies, then I should be able to get a better accuracy in terms of the variance. And now, but if you look at these numbers, that essentially it's possible to achieve the standard limit something like 4 over n. Well, I mean, or you can just say it's just 1 over n. And you can see that we have deliberately chosen this term here so that beta is greater or equal to 1, so that this term cannot really asymptotically add much to the. So this is a dominant term. So we have by choosing beta to be bigger than 1, we have make sure that the first term is the dominant term, so that we can't compensate this. We cannot explain how you can obtain something which is better than what you are supposed to have in the standard limit. Okay, so this implies that alpha has to be less or equal to 1, so that this additional noise will, when you add up together, it will be obey the standard quantum limit. Okay, now for the probabilistic case, we have to be a little bit careful, and let me go back a little bit here. And in the probabilistic case, that this is no longer just a simple kind of a trace preserving quantum operation. This is should be replaced by the result of a projected state. So you go through some process and you do a measurement, and if it's yes, then you use it. If it's no, then you don't use it. And so this would correspond to the outcome of the state when you get a yes answer, saying that's true. And now
allow it with the probability which is arbitrarily.
Yeah, you will see that it's going to be small. It's going to be small. Now here is a crucial argument that we have to be careful about, namely that we cannot use the best entangled measurement on this thing here. Now, what this formula works is because of the linearity. You know that if you do each copy individually, and then the variance will come out to be a kind of linear in terms of the probability distribution. So therefore, this trace condition ensures you that you can say something like this. And if you do an arbitrary entangled measurement again, then you will not be able to make this statement true. And so the point after all this is that on this side, you still put the kind of the standard quantum limit, except this case is for a quadratic number of copies. So therefore, you still get this, and this basically is n to the minus alpha, because alpha is if it's bigger than 1. And now here's another term, which is another, could be, if beta is equal to 1, you could get n to the minus alpha. But this cannot be better than the Heisenberg limit, which is n to the minus a half, n to the minus 2. So therefore, this says that this alpha has to be less than or equal to 2. And here, what about this assumption here? That suppose I'm interested in things not in the asymptotic limit goes to 0, but I'm interested in something like 1% or 2%. Then this argument will not work. And so this derivation here says that the Heisenberg limit under certain conditions will give us the optimal, the kind of the upper bound. But actually, once we know that this result is likely to be true, let's go back to the beginning and let's forget about the Heisenberg limit and let's go to the problem itself. And it turns out that if you analyze it laboriously, you'll be able to show that this condition is not there. So therefore, the theorem that we say is true without this qualification. And so what we have done so far is that we are interested in some fundamental limits to the replication rates of the clock states. And we have asserted that the deterministic process is bounded by 1 and the probabilistic process is bounded by 2. And we gave a intuitive derivation of why this limit is true. And now we're going to show that this actually can be done. And now, so here's the clock states. And it turns out that it's possible to devise a probabilistic process so that if the projection gives you the answer yes, actually the state is so good so that the fidelity is exponentially close to the I mean, all this H is a fixed Hamiltonian, and so this is everything is constant except n and m. So essentially, this is the term that the how close it is to 1 in fidelity is bounded by exponential to the minus n squared over m. So it means that if m is less than quadratic, then you can design a process so that it's reliable. And actually, it's not only good fidelity, but it's exponentially good fidelity. And the proof idea, actually the proof is not difficult. Can be explained in a few words. Basically, we go to the Fourier space. We go to the look at the spectrum of the energy for it. So the original state will be kind of in this, and now the output desired will be for bigger m. So m could be, so this would be much larger than that. But let's say that m is less than n quadratic. Then if you look at the relevant part of the spectrum, then if you just restrict yourself to a segment in the middle about of size n, then that would be exponentially close to the state, so that you don't need to worry about the tail. You only need to worry about something like square root of m of this. So the rest will be exponentially small. And now the good thing about the so how do you transform? How do you do probabilistic process so that this can be sort of equal to the important part of the amplitude? Well, it's actually very easy because if you don't care about the probability of success, as long as you have enough of the spectrum, if the range is wide enough, you can do a projection so that it will be kind of mimicking the important segment of the. And so the idea is that it's possible to design a probabilistic filter so that for different kind of energy state, you can scale it by the right amount so that when you take this thing after the projection, it will become exactly the central part of the spectrum. It's yes. Oh, good. Okay, so it's really just the central limit theorem, and so one can say that this is a sort of a super replication, and this process can duplicate the number of copies with almost no error, and so we can call it super replication if the rate is bigger than 1. So if you put in some numbers, it actually looks pretty good. So if n is like 100, but nothing that you can probably achieve in the lab, you can have. But
what's the probability that that process?
I'm going to come to that. Yeah, I saved the bad news to the end.
All right.
And so so there are actually even more compared with the deterministic case, that it's possible to show that in the deterministic case you will never be able to achieve the probabilistic fidelity close to it has to scale like a polynomial. So all these are the good news. Now here's the bad news: is that it comes with a cost, namely that the probability of success is small. And now for our scheme, it's you can see that when you try to flatten or expand the amplitude each time for each energy kind of in the spectrum, it gives you a factor. So altogether, you get an exponential factor of success. And actually, one can prove a theorem saying that this is inevitable. So as long as you are interested in super replication, namely that you like to produce more than linear number of copies, then the probability of success has to vanish exponentially, like the following, and otherwise the fidelity will go to 0. And now let me stress that the super replication will only demonstrate it for one particular interesting family, class of a family of states. And now let me just remind you that it's not possible to have universal super application, and I think it's known to the experts in the field for a long time that if you are interested in a universal replicator good for all the states, then probabilistic cloning doesn't help you in any way because of some symmetry reasons. So in conclusion, it's very simple that we have studied a family of quantum cloning, especially about the limit in the probabilistic case, and we have remarked that the super replication is not a generic phenomena, and I think that we still don't understand a lot of things, and specifically that we don't really know what kind of states for which that the phenomena of super replication can exist. So before I end, let me just say a few things. I think yesterday at the restaurant, I think people have said, so I'll take this opportunity just to say a few words. And I think the world has changed a lot, and especially when I look at this no cloning theory in 1982, and it reminded me of the days, say in 1982. I was at Berkeley, and actually I met Umesh for the first time in that, and we were doing, I think we were doing wonderful things, because that was the beginning of that people realized that theory computation can be used for cryptography. And now, at that time, we had no idea that some wonderful things is happening in other places that are very close in spirit, like the no cloning theorem. And so that was the time the no cloning theorem and other work have ushered in a good, prosperity period of quantum information theory, and that's why we are all here. And also this center, this quantum center is located in the rationality center. I think, Gil, you're part of it, right? I think Michael Benoit is a part of it. So, exactly in 1981, there was a classic paper, a kind of a Nobel Prize winning paper by Roger Myerson on auction theory. And if you look at this paper, and it's exactly the kind of thing that we love to do. So at that time, we live in a different world. And I think that it's amazing that today here, I think there are many people here who feel very free in working in any of this subject and possibly in evolutionary biology and here. So I think the good time is upon us. It came a little bit too late for me, but I just wrote a paper on auction, so I think that I'm enjoying the fruits too. So in parting, I would just like to congratulate you on the inauguration of this center, and I wish the center prospers, and together with the Institute for Advanced Study. Thank you very much.
Thank you for, I really enjoyed the talk. Can you give an example for a realization of a super-replicator the same way that you gave the example of the amplifier for a standard replicator? Is the daemon simple to explain, or is it like very complicated configurations?
I think that we gave the construction of the probabilistic transformation. So it's a very difficult experiment because it involves manipulating the many photon states. So the maximum daemon is really doing a projection to for this state in each of the energy plates to project it so that the amplitude will look like this. So basically, you need to you can modulate the amplitude by using some auxiliary part, so that when you do the projection, you will only get a certain fraction of the amplitude, so that will satisfy this condition. So in this case, the process is absolutely simple, but it has no problem for Maxwell daemon to do it. But I think that for our lab, unfortunately, I'm not sure. Yeah.
More questions?
We know that deterministic cloning allows you to solve the NP-hard problems. So I was wondering, is that okay?
Sure.
So I was wondering if you could use this principle to show that probabilistic cloning is impossible.
I don't know the answer. Actually, I don't know how you prove that the perfect cloning solved the NP problem, except that, you know, if you do perfect cloning, you can do even more amazing things. I mean, how do you do it exactly?
Sorry, how do you show that cloning allows you to solve
NP? Yes, the satisfiability problem.
Well, I can try. I'm not sure if that's.
Yeah, probably don't have time. Maybe you can talk.
It's not that. You want to?
Well, I mean, it depends exactly what the model is, what's allowed. Like, if you can clone repeatedly in superposition, then you basically just have a nonlinear quantum mechanics.
But even but even simpler than that, you take a SAT formula and make it accept, like add something that allows half of the configurations to be accepted. So now the formula, whether it was satisfiable or not satisfiable, now it becomes satisfiable with. So if you measure so you create a. Well, you write the answer, then you don't measure it, you clone it, so now you can...
Yes, well, I imagine from what you said that it sounds like approximate cloning should be able to do it. I think that I mean, if its fidelity is good enough or something.
The problem is that you're saying that the probability of acceptance could be exponentially small, so this process would take
but the important thing is that they need to be, I think that they need to be independent. I think that that you need to create a cloning which are exponentially close to the original one. In addition, they have to be independent. I think that if they are independent, I don't see why the kind of thing that you say. Is that right?
Well, no, I could easily believe that this sort of thing would let you solve an NP-complete problem with exponentially small probabilities. And I know other ways to do that also, but yeah.
Yeah, so it's not...
So that's why it's not convincing.
I mean, that's why it's not that exciting.
Yeah, but cloning allows you to do that in polynomial time, right? The deterministic cloning does allow you to do that in...
but we know that it cannot do it. Yeah.
So, from a practical perspective, how threatening are these cloning techniques for quantum key exchange, for instance? Is this an open problem? Are there already known results?
I think there's no known result because I think that that we have not analyzed it, and I don't think that it's being analyzed yet.
Do you think it could have applications? So, you know, the BB84 protocol, for instance.
Yeah, I think that's getting a little bit kind of detailed in terms of the numbers, and I don't know, I have no idea how the numbers would work out compared to, you know, the standard way of doing the attack.
Okay, thanks.
Any more questions? I have a question. So you were using the central limit theory, which applies for, say, spectrum which are well behaved, have second moments. Could you think of states which are not so well behaved, Lorentzians or so?
I mean, if it's
if they have fat tails.
If have fat tails, we have not looked at it. I think I think it probably doesn't work. I think that if you have coherent state, I think that Julio has some results saying that you will not be able to have a super cloning. I think that for some of those states, so it has to be finite for our case.
Okay, let's thank Andrew again.
נורידו 5 דקות על זה. מה, איזה בעיה זה עושה?
לא, עדיף לבוא עם קובץ.
לא הייתי מודע.
Okay, so the next talk is by Adi Stern from Weizmann, and he'll talk about topological aspects of quantum computation.
Thank you and good morning. And I'd like to follow the previous speaker by congratulating my friends from the Hebrew University for this for the inauguration of this center. It's about 40 to 60 minutes from here to my home or office. So I hope to enjoy this center as well. So I'll tell you a few things about topological quantum computation, about some new developments. And my studies are funded mostly by the BSF and by Microsoft. My plan is this. I'll start by introducing topological states of matter, giving some basic concepts. Mostly I'll focus on anyons, and in particular on non-abelian anyons, which are the building blocks of topological quantum computation. Then I'll tell you a few things about topological quantum computation, and then the main part of the talk will be talking a little bit about Majorana fermions, and where you can create them in an experimental system, and going beyond Majorana fermions and trying to think about schemes which are more powerful than those you can achieve by using Majorana fermions. Now this will be a short talk, so if you'd like to hear more, I've been involved in writing some review papers two introductory ones, of which the last one is in Science a few months ago, which mostly focus on aspects of topological quantum computation. Also, as may have been mentioned here, there will be in a few months, right at this hall, I believe, a winter school on quantum computation, which will include a part on topological quantum computation. The starting point, talking about topological states of matter,